today we should be looking at the note, this one on double right triangles, and we're going to do 2 questions together, and then there's a bunch to do on your own, or sometimes a little bit longer than the other ones, although solving a triangle has a lot of work to it as well. And the idea behind a double triangle, and I suppose these could even have like 3 triangles or more, but the idea is, whoops, frozen, is that you have more than one triangle, but they always share a side, or maybe they share more than one side, or they share an angle or something like that. So it's one figure, but it has multiple shapes in it. And in fact, this has 3 triangles, right? Do you see where the 3 triangles are? 1, 2, where's the third? It's this big one, right? Now the big one is not a right triangle, so we haven't started doing that yet, but next week we will. And in that case, maybe you can use some of that stuff as well, but sometimes you can just do it with right triangles. This is missing a little symbol. We should add it in because these are both supposed to be right angles. Should be part of the diagram, but we'll label it now. And the idea behind these is problem solving. No 2 questions will be identical. So here's the things that we need to know. You might ask these questions to yourself as you're starting. Like, you might not actually ask them in words, but this is the kind of thing that you should be thinking. What can you find? What is helpful? Because there's lots of things you can find. Some of it will be helpful and some of it won't. And what would you need to solve? This first question's not super clear. This first question, is a bit easier than some of the ones you're going to do because it kind of does the thinking for us. But for example, if I didn't have x here and I only had to find theta, I can't find it directly with the information that I'm given. So then I would ask, well, with this side length and this angle, what could I find? I can't find theta. What could I find? So I could find this, which is x, which, very good. Yeah, so even if x wasn't there, you might have to find it anyway. Sarah? Nice. Well, I could at least find this one. I don't know if I can find this one yet, but you're right. I could find this one. Let me mark some of this down. So I could find this angle. I could find this side length. What else could I find? If we just look at the triangle on the left, what's left? Yeah, the diagonal part. Can I find that with the information that I'm given?
Once you find the middle line.
Hold on. Now, we're not at that stage yet. What can we find directly? And I think we can find, if we wanted to, we could find that. Is it helpful to find this? I don't think so. Is it helpful to find this? Depending on how you solve the question, maybe. But of the things that we can find, the most helpful, I think, is x. Why? Because and this is where, what would you need to solve? If I was looking for theta, well, if I had x, then I would have 2 sides, and I can use 2 sides to find an angle. So some people find this stuff harder because it doesn't tell you directly what to do. You have to figure out what you can find and what's useful in order to find, in this case, let's say theta. And that means when you're using SOHCAHTOA or when we do the other stuff, sine law and cosine law down the road, when we're doing that, you have to know, what do I need to use SOHCAHTOA to find an angle? Well, you need two side lengths. All three of the ratios, they're all the same. They have one angle and two side lengths. Not the same side lengths, but that's what they have. One angle and two side lengths. If I have any two of those things, I can find the third. If I have two side lengths, I can find an angle. If I have an angle and a side length, I can find the other side length. So this is a big part of mathematics, is knowing what you need to use a formula. And if I'm trying to find theta, what I would need is two side lengths, but I only have one of them. So if I find x first, then I have what I need to find theta. That's the kind of thinking that you do in problem solving. Whether it's these ones where the figure is given and it's not like a word problem, we just call them double triangle problems. Or whether it's an application, and we'll do some applications that involve this stuff as well. And in that case, it's the same thing. What information do you have? How can you use that? What do you need to find in order to answer the question? That kind of stuff. Okay, so let's get started. We're going to find x. In other words, we're going to find x first. And we're going to do it the same way that we solve triangles, where we're going to try to communicate what we're doing where. A little title like this is going to help clarify what you're trying to do. So for x, what's the first step when we're doing this stuff? Label. Thank you very much. And so I'm working in triangle number 1. If I call this triangle number 1, that's where I'm working right now. So I go across from the right angle is the hypotenuse. Across from the angle, so because I'm given 71, I'm just going to use that one, is opposite. And the last one is adjacent. Remember we did this trick yesterday where you can circle and circle. I'm looking for x and I know adjacent. I'm looking for opposite. So that is which of the three ratios. Which one's opposite and adjacent? Alexis, you know? Tan, thank you. Write out the formula. One of the reasons why we like to see this formula in trigonometry is because this is you showing which of the three ratios you're going to use. And picking the right ratio is usually worth a mark. So write out the formula before you use it. It's short, so it's easy to write out. It's not like quadratic formula that takes a long time. So the angle is 71 because that's how I labeled the triangle. Opposite is the x. And adjacent is the 10. And then what do I do here? I multiply both sides by 10, so I bring the 10 over. Just as an aside, put your pencil down and watch for a second. If I had x over 3 equals 5, what number divided by 3 gives you 5? How do I figure that out? I multiply both sides by 3. We did this yesterday, I know, but I want to show you again. So these divide to 1, and I get x is 5 times 3. It's the same thing that we're doing here. I'm dividing by 10, so I multiply both sides by 10, but it clears out on the one side, and I end up with just 10 multiplied on the other side. Because with trigonometry, we're always doing the same thing over and over again, we start skipping thinking about why we're doing it, but always remember that there's a why. And then I'm going to go over to my calculator, and I type in, on this one, every calculator is a little bit different, but this one is 10, tan, and sometimes you need a bracket. Some calculators do a bracket for you, some don't, and 71. And remember, we also talked yesterday about how your calculator's got to be in the right mode. And mine is, I wonder if you can see better if I zoom in. You can kind of see the D there. And then I just hit equals. And there's my answer. And so that means, whoops. x equals, now I'm going to do two things. Because I'm going to use this answer later in the question, I'm going to write it down with 4 decimal places. But the instructions say 1. But we're going to need 4 to safely get the next right answer. So I'm going to write that down, and then I'm going to round it properly, which would be 29.0, because it asks for 1 decimal place. Next thing we need to find is theta. And it's not always the case that you could just find it directly. I might need to do another step before I find theta. Like there could be questions that have 3 parts. The other thing we want to think about is because I'm in a different triangle, I have to relabel. So take a look up here. This side length is opposite of 71, but it's adjacent of this angle, right? And, but if I move to the other triangle, it's opposite and adjacent to different angles. Again, I'm in a different triangle. So just because I labeled this as opposite doesn't mean it's opposite for everything. Now in this case, we're finding theta. And this is, again, opposite of theta. So it is opposite again, but you always have to rethink. Once you're starting over in a new triangle or with a new angle, you always have to rethink if you have to relabel your sides. So I'm looking for, oops, I didn't actually write this one down. This one's supposed to be hypotenuse, right? And this would be adjacent down here. So I'm looking for, I have hypotenuse. I'm looking for opposite. Which one is opposite and hypotenuse? Sarah? Sine. Very good. So for theta, we're going to use sine. Opposite is the x that I found. So I'm going to write out all 4 decimal places. If you don't do that, people always ask, do we have to do that? What if I just use 29.0? Sometimes you'll get the exact same answer. Sometimes you'll be off by a decimal place. So if you're off by a decimal place, you might lose half a mark. So you're kind of, risking it if you don't do that. So if you use 4 decimal places, you'll always be fine. I'll show you another trick. If you have a good calculator and you want to get to know how to use it, my calculator keeps this answer inside, and I can actually go, so we're doing shift sine for this one because we're looking for an angle, and if I hit this answer button, it puts the last answer from the calculator in that spot. And then there's no rounding. So if that makes sense to you, if you like that idea, you can do that, or you can keep 4 decimal places divided by 37. So in my calculator, this is how I put it in. Shift sine, you need a bracket here. So if your calculator doesn't do one for you, you do it. 29.0421 divided by 37. Hit equals, I got 51.7. Which is approximately 52 degrees. And we usually round angles to the nearest degree, and that's what it said in the instructions, so 52. All right, we're going to try one more. The other thing is we have to find x and y. You may not know right away how to do both of them. But if you know one of them, then do it. If you can't figure out what to do at all, then ask yourself, well, what can I find? And just find it. Label it in your diagram and see if that helps. Okay? What do you think we can do here? Anybody have any ideas? Eunice? How could I do that? The top angle? How could I do that? Yes, good call. It's not labeled. Right. So subtract them both.
Yeah.
Because that angle for this big triangle, that angle is 40. It's 10 plus 30. You would add them together. Very good. So I'm actually going to start with that. I'm going to find that angle and I'm going to mark it. This is 40 degrees. And I could find that, which may or may not be helpful. I don't know. Might be helpful, might not.
Would you find, okay, so would you find the y?
Can we find y?
Yeah.
How come you think we can find y? Right, because now we have this angle 40, which is in the big triangle. And in fact, what I'm going to do, just in case anybody doesn't quite see it, some of us are very visual and some of us are not. I'm going to redraw this triangle. Sometimes it's really helpful to redraw just one of the triangles off to the side and label it. So this would be y, this would be 12.7, and this would be 40 degrees. And now I don't have any of the other junk, which would really just be this line here. And as Brooke said, I have enough information to find y. I've got one angle and one side length, and it's 90 degrees, so I can find y. And that's one of the things we have to find, so let's go ahead and do that. So for y, and so I'm going to label, and you can either label the original diagram or your new one if you want. Hypotenuse, opposite, and adjacent. Yes?
You're just going out to make like a big, the outside triangle.
That's right. Yeah. So I've got opposite and adjacent, and that is tangent. Tan. And it's really important that you know what angle you're using. Some people maybe go too fast and don't think about it carefully enough, and they use one of the other angles like 30 in there. Okay, but I want tan of 40 equals opposite, which is y, if we look at our new diagram, over adjacent, which is 12.7. So again, I take the 12.7 and I multiply on the other side. And I put that into my calculator, 12.7 tan 40. And I'm going to write down 4 decimal places in case I need to use this. But then I'm going to round it because it says round to 1 decimal place. And it's centimeters. I think I forgot to put units on the last one. I should go back and do that, but try to remember to put your units in. What do you think? Yes?
Wait, is that only for the right triangle going down?
Yeah, this is, once has everybody got that down okay? What we just found is y for both triangles because it's kind of the same. So I found this length, but hold on. It's the same as that length, right? So I've got y. How many people think they have an idea of what you do next? I think Eunice does. Yeah, you do. Okay, good. Very good. That's fantastic. What do you think?
Oh, I was just confused. Like, I thought you were just drawing like that smaller triangle on the bottom, so you have to use the 30 instead of the 40. But
Right. I was finding this y. But if I used 30, what would I have found? It doesn't have a variable.
oh no, it's not right.
Yeah, the bottom half, right? What do you think? So I would have found that. Let's call it A. If I had used 30, you're saying I would have found that length A. Brooke, what do you think?
Well, you can find that and then subtract.
Very good. So the only way to find X for us is by finding A. And if it doesn't have a variable, give it a variable. Put it in the diagram. We're going to find A, and then if we do Y minus A, that'll give us X. Now we have a plan. And some of you may have known that from the beginning that that's what we're going to do. Some people don't always see it when you're doing the subtracting or adding type of questions. If you did from the very beginning, that's great. But notice, We weren't worried about that before. We were just worried about finding y. And sometimes you might have to do that. You might be like, well, I don't know how to find x, but I'll find something else and see if it helps. But the best thing is if you can see a few steps ahead to figure it out. So now we're going to find a first. And we kind of already talked about this, but I will redo it. So I'm going to use, for a, for this triangle, there's the hypotenuse. Ooh, I could redraw this one. Let's do that. So this is now 30 degrees, and this is A, and this is still 12.7. And I've got hypotenuse, and I've got opposite, and the last one is adjacent. And again, it's tangent. Plug it in my calculator, and I got 7.3323. Now this isn't one of the things I was asked to find, so I don't need to round that anymore. I can just leave it like that. And then again, the last step for x. X is going to be equal. Let's just look at this to make sure everybody understands. If y goes this whole direction, then if I take away a, I'll be left with x. Because x and a make up y. And there was no way with SOHCAHTOA at least to find x directly. And I'm going to use those 4 decimal place numbers, 6566 minus 7.332. 23. And I got 3.3 centimeters rounded to 1 decimal place. And what's interesting, and this is one of these cases where if I use 10.7 and subtracted 7.3, I would get 3.4. So it'd be off by a tenth of a centimeter. Yeah, a tenth of a centimeter, which is not very much. That's a millimeter. So again, if I use this rounded answer and subtracted this 7.3, I wouldn't have got 3.3. Does that matter? Does it matter just because it's math class? Like, why do we care about a millimeter?
Because it's just using the real world, it wouldn't fit or it'd be off by a number.
Now, if you're working with wood, if you're finishing your basement or building a house, you probably don't care about a millimeter. If it's a little bit long by a millimeter, you take your hammer and you hit it, and it fits in there, right? Or you shim it or something like that. Or a millimeter, wood binds together so nicely. You screw it and it's solid. So it totally depends on what you're doing in the real world. If you're building out of wood, you may not care. If you're building a finely carved special ring box for your engagement, you might care about a millimeter because it might be showing a gap and it might look nice. Maybe I've said this before. I usually make the example of a spaceship. If you're building a spaceship, a millimeter might matter because the panels don't quite match and that ship goes into outer space and then it decompresses and air starts getting out of the spaceship, then the people on the ship die. So a millimeter might matter. And there was a famous explosion that killed the astronauts that were on board where it was because the panel wasn't the right size and it didn't quite fit or something like that, I think, is what happened. One of the panels was off by not a lot. If you're building a bridge that's 200 meters across, will 1 millimeter matter? Maybe not. Like if you're figuring out how much cement there is or something, probably not. 1 millimeter over 200 meters of cement probably won't matter. But that's up to the engineers, the people who are building it, who have the experience in that particular situation. That's up for them to decide. I do think it's important that we know when we've got a perfect answer or when our answer might be off by a bit. That's our goal in math. And if our answer is off by a bit, but we don't care because it's like, well, what difference does it make? It's just wood. That's fine. But we will try for perfection. Any questions on